Okay. So we continue the discussion on partial, what is this, partial transpose. Before that, I want to give an assignment. So this is assignment. I have already given assignment on this Weil-Heisenberg operator. Okay. This is some continuation of that. If X is in L of CD, just a D cross D matrix, if you have a D cross D matrix, then X transpose is equal to summation summation X Y equal to 1 to D, whatever. I mean, it is indexed by 1 to D, the orthonormal basis, the dimension is X equal to 1 to D, okay, and E over 2 pi I XY by D. There is a 1 by D here, okay, and this is just a number. Then WXY, you know WXY, which is UX times UY. I defined it. If you remember, you have orthonormal basis E1 up to, or if you have orthonormal basis I, then UX acting on that is UI 2 pi X. I mean, sorry, if it is Y, I mean, I mean, this is square root of -1. So XY by D times the same thing. And another thing, Vy will acting on any Z is just Z plus Y. This is just a permutation matrix. That is just a diagonal matrix with all these things. So which we have defined. These are these. I have given an assignment. These satisfy some Weil commutation relation and all that. This is one more thing. You have W of XY, X. This is star and W of X minus Y. Okay. That's all. It's clear, no? I mean, this is number. This is operator. This is operator. Okay. Minus. So this is the assignment. It is just checking. That's all. Just checking all the multiplication. That's all. Okay. Okay. Now we want to define what is called positive partial trace states. Okay. So definition: X is a row. Row is a state in HA, tensor HB. Okay. Row is a state. Is a state. A state means it is just a matrix which is positive and trace of row is 1. Okay. That's all a state is. Okay. Then is said to be a positive partial trace state. Short term PPT state. Okay, PPT state. If you take the trace B or trace A, doesn't matter. Trace B of row is positive, is also positive. Row is positive, you take the trace over one component, that's also positive. Okay. Proposition: if row is PPT, then we have defined it through B, it doesn't matter, that's what we say. Trace A of row is also positive. Further, whatever it means, the positivity, I mean, the positivity does not, whatever the partial trace positive, I mean, trace is with respect to some orthonormal basis. You can fix another orthonormal basis and write the matrix with respect to that, and then take the trace. That will also be positive. So this trace, I mean, if you have another, what I want to say is trace A row greater than 0. The trace row greater than 0 does not depend on, or the PPT property. Let me just write it and I will explain it in the proposition. PPT, positive partial trace property, does not depend on orthonormal basis. Depend on orthonormal basis. Okay? It is with respect to any other orthonormal basis also, it is true. So proof. What we have to prove, you will just write it down and it will be clear in the proof. Okay. The first one, if we take that, so it is trace, partial trace with respect to B is positive. Then we want to prove partial trace with respect to A is also positive. So trace A of row trace we want to consider trace A of rho. Trace, we have trace B row is greater than 0. This is a matrix. Huh? Sorry, it is transpose. It is transpose. Sorry. I have transpose in mind and I have been saying trace. I'm sorry. Yeah, it is transpose. So I have to say sorry. So when I do that, it will be clear. When I write it, it's clear. I don't know why I am saying all these things. Sorry. This is just transpose. Okay. So this is our TB, right? Sorry. It is transpose only. I don't know. I have been saying trace all the time. Okay. Yeah. Because we have two things. So if rho is a state which is its trace rho equal to 1, it is positive if TB rho is greater than or equal to 1. That's what it means. Okay. Sorry. Yeah, when we write the condition, everything it will be for transpose only. Okay. So then TA rho, if you take the transpose with respect to rho, that is also positive. That's what this says. And the PPT partial transpose property. Sorry. Here also, I'm sorry. I'm extremely sorry. I have to change the whole thing. Okay. Let me start it again. Rho is a state, okay, then which satisfies this property is positive partial transpose state, PPT state, if if you take the partial transpose with respect to B, that is positive. Okay. We want to prove that if you take the partial transpose with respect to A, that is also positive. That's what we want to say. And further, the PPT property does not depend on the orthonormal basis with respect to which the transpose is taken. You can take the transpose with respect to, of course, trace is always, trace is well-defined property. It does not depend on orthonormal basis. We have shown on that. So it's only for the transpose. Transpose depends on orthonormal basis. But in this case, the positivity of the transpose does not depend on which particular orthonormal basis. That's all. Okay? And you should remember that transpose is not a completely positive math. Okay? So that's why if you take one tensor that may not be positive. This is the definition is because of that. There are cases where this is not satisfied. Okay, TB of rho is greater than or equal to 0. Now, if you want to take, so now TB of rho is greater than 0. Now you can take transpose of this whole matrix. If something is positive, then the transpose is also positive. That is TB rho transpose is also positive. This is the usual transpose, not positive, usual transpose. But this usual transpose is going to be TA, tensor TB, not TA transpose TB. It is just that transpose taken in both the components. So TB rho, TB rho transpose is equal to, it is just TA tensor TB. It's a transpose in A component, tensor transpose in B component, and transpose in B component twice it becomes identity. So it is just transpose A. So this is also positive. So if the one component trace is positive, it's positive in the other component also, provided rho is positive. Okay. Now we will prove the orthonormal basis property. So to prove TA rho being, it's not, TA rho will not be equal to, that will depend on the orthonormal basis. TA rho will depend on orthonormal basis, but that being positive is not depending on orthonormal basis. So to prove to prove that it does not depend on orthonormal basis, if TA rho is greater than 0, then we want to take transpose with respect to some other orthonormal basis that should also be positive. So if EK is fine. EK and K equal to 0. Let us work with it's B, no? dB minus 1. Okay, some other orthonormal basis. We have fixed orthonormal basis, that is I, ranging from 0 to dB minus 1. Here I am taking EK minus 1 and orthonormal basis for HB. Okay. Then we need to prove the following. Summation 1 tensor, where this is over K and L. K and L, E, K. If you have written the matrix with respect to K index the row and L index the column, here it will be LK. Okay. times rho times 1 tensor again EL Ek. This is positive, right? That's what we want to prove. Is that right? We want to, this is just the transpose taken the second component where the sum is over there. I mean, in general, this is the transpose. You can take any orthogonal basis, then you take these vectors and hit with those two vectors on both sides, then take the summation, that will give the transpose. If row, I mean, in this row, I mean, row is this row, rows are indexed by K and columns are indexed by L. Okay, then this is the case. So this is what we want to prove. But we have TA row is greater than 0. So TA row, let us compute. TA row is equal to summation over I and J. Okay, 1 tensor. This is the usual orthogonal basis, standard orthogonal basis. So this should be J and I. I indexes the row and J index the columns. IJ row. And then here we have again 1 tensor. This is 1A tensor Ji. Okay, this is greater than or equal to 0. That's what we have. Okay, now we want to compute this. We have this. We have another thing, that summation over EL E yeah EL okay, L equal to 0 to dB minus 1. This is equal to 1, of course. This is just the identity operator. So I insert that operator here and here. Okay, that's what I want to do. So this is equal to summation over I and J. Okay, I and J 1A tensor, okay, J I. So here I take the summation over KL. I mean, I will insert this operator. This is the identity operator here and here. So I take the one I index with L, another I index with K, and take out the whole summation. Okay, so this is equal to summation over I J K L. Okay, I index with K one. I mean, one summation with K and I insert here. One summation with L I insert here. Okay, that's okay. Should I need L there or K? This is okay, I think. Okay, if it's not, we will interchange K and L. Doesn't matter. We will interchange. We will assume that row is interchange. I mean, indexed in a different way. Okay, we don't care about that. Okay, this is equal to this. This 1A tensor. Okay, J I. Okay. Now here, I mean, this is 1. So I want to insert 1 tensor here. Okay, so it will just come here. So which is just EL, okay, EL, okay, and then row here, then 1A tensor, the same J I. This is right. Then E. I have it before this. E K E K. Okay. Then J. Okay, it's fine. I just inserted it. I haven't done anything. Okay. In this is a scalar. Okay, IEL is a scalar, and similarly EKJ is a scalar. This scalar I can take it to this J, and similarly IEL, this I take it to this I. Okay, so I write it like this: summation over I J K L. Okay, 1A tensor. I want to take this scalar. Where is this scalar? I mean this EKJ. I want to take it with this J. Okay, so inner product EKJ with J. Okay. This is just a constant. These are all scalars times J. Okay, I have this. Then I have I there. That IL will go there. EKJ, and then EL is there, of course. Yeah, and EL is there. EK will come here. EKJ. This is fine. Okay. Yeah, this is fine. We have the sum. EKJ, I have taken it with J, and IEL, I have to take it here. This is also scalar, and this EL, I have kept it there. So there is no problem. Okay, and there is a row here. And then here we have 1A. I mean, we are just passing through this tensor. The second component, we are just passing it through. Okay, so I have IEL, which I want to bring it here. So I have EK, okay, and IEL, inner product with I and EL acting on I this way, sorry, I this vector. Is okay? Okay? Okay. Now I take the summation, these are all finite summation, we can interchange. Now I fix the KL summation here, I take the J summation here, there is no J anywhere else, I take the J summation here. And I take the I summation here, okay? So let us compute it separately, okay? So EK, J, J, this summation over J, 0 to dB minus 1, this summation, okay? Now this is equal to, this is just the bar of the other way, but then you can take the bar inside. These are all, I mean, we are having Euclidean inner product. So we can, these are all having, if you have some EK, then you can define EK bar, where you, this is just coordinate. So I mean, we are just working with that. Coordinates wise bar you can take, that you call it as EK bar. Okay. So this is equal to J bar is J. This is just 1 at the jth place, everywhere else 0. So it is J bar is J, and you will have EK bar here. And then you have J here. J is the other way, sorry. J is this J. Sorry. J is this J. That's what I have there. So J here. Okay. Now this is just EK bar. This is just the summation, expansion over the orthonormal basis, that is equal to this. Okay. This is the EK bar. Just the orthonormal basis expansion of that. Okay. Now you consider that. What is the other one? The other one is I, EL, and then I here. But this is just the star of, if you take the star of this, that will become the other vector, whatever that vector, the ket vector, let's say ket vector, no? And this will become, you will take the bar here and it will become EL, I mean, it will become IEL bar again. Okay? If you take the bar there, it will just IEL bar. Okay. And then you have I here, whole thing star. Okay. Now you can take the summation inside, you can take the summation here, you can take the summation inside, and this will be just, you will only get EL thing, and you will get the, I mean, this will become this. Okay. You will actually get inside this EL bar vector. When you take the star, it becomes this. Okay. So this is what, so this is the computation. So the result we get is summation over ij summation has been taken. It is just KL and then 1A tensor, and all these things have gone. So this is just, you get EK bar, right? EK bar, EK, right? And then row here, then 1A tensor, EK bar, EL, sorry, EL, EK bar, EL. Okay. And there we have EL, EK bar, right? There what will we get? EK, EL bar. So EK, EL bar. EL bar. This is EL country. Okay. Okay. Things fine. புரிய முடியாது. சாரி, சரணியை ஆபரேஷன் பண்ணிட்டு புரிய முடியாது என்னால. இதெல்லாம் இருக்கு. Thanks. Okay, so what we have got is the following. So we have got this. Let me just write it here. Okay. What we got is 1A tensor EK bar EL. We are supposed to have EL. I mean, this is what we have is the following: EK bar EL rho 1A tensor EK EL bar. Okay. This is equal to what we have computed. It's as TA of rho. Okay. The same TA of rho, where the transpose is taken with respect to the standard orthonormal basis, we have written it with respect to this basis, this new basis. Okay. Now you want to have EK bar, you want to remove this EK bar. You want to get EK here and you want to get EL here. You just use a unitary to do that. So you take the unitary, which is equal to summation K equal to 0 to dA minus 1. You want to bring this to EK. Okay, so what do you do is you take a you just take it to B. I mean, notice that this is also an ENB, right? EK is, this is also ONB. EK is ONB means EK bar is also ONB. It is just the bar and that's clear. Okay. So you have this EK bar and EK. If it is EK, if it is just EK everywhere, that's just identity matrix. But instead you have EK bar EK. This is a orthonormal basis. This is an orthonormal basis. This unitary takes this orthonormal basis to this orthonormal basis. Okay, that's what this unitary is. Just the conjugation. That's what it does. So if you apply now, you apply U T A rho U star. Okay. Now this is what you get. You get 1A tensor. If you apply this EK bar here, EK bar here. I mean, only when, I mean, this is just summation K. This K will not come here. I mean, this, sorry, there is a summation here. Summation over K and L. This is equal to summation over K and L. But now you have a summation over K prime, L prime. You have a, I mean, U will have a summation. U is this. U star is this with the star there inside. So there will be a summation over K, K prime. There will be a summation over L prime. You hit it here with a summation over K prime. So it will pick only the when K equal to K prime. This, okay. So you will get EK bar. What I am saying is, if you apply this, multiply this, you will get EK and whatever that EL, that will remain as EL, okay, times rho. And then you are hitting it here, that will pick precisely when it is equal to L. Okay. So this is equal to 1A tensor, again, EK, EL. That's all. This is what the transpose with respect to that new orthonormal basis by definition. Okay. Now, if TA rho is positive, this is also positive, right? TA rho is positive, implies it's actually equivalent. U of TA rho, U star is also positive. Okay. So this, if you have any X is positive, then U star is also positive. You use the directly definition, or you can write it as U X power half U. So this is in the form of X star X, and because of that, it's positive. Okay. So we approved. Okay. So we approved the proposition. Okay. So this is about, this says that PPT does not depend on orthonormal basis. Okay. Now we make another proposition. If rho is a separable state, rho, you have to say in L of HA tensor HB is separable. It's a state and it is separable. Okay? Separable state. Then it is PPT. Okay. Proof. Rho is separable. That means rho looks like this, right? Pi, some omega AI tensor omega bi, right? That's how it looks like, where omega ai is a state, omega bi is a state, and summation pi equal to 1. That is what definition of separability is. Okay. Now, if you want to take T B of rho, that is just going to be pi omega ai, then omega bi transpose. If something is a state, its transpose is also a state. It trace and transpose. When positivity of the transpose does not depend. I mean, it is invariant under transpose. Something is positive, transpose is positive. Some trace is same for T x and x transpose. Because of that, this is also. I mean, this is also a state. Okay. It's also positive. This is also positive. So that's what we want to prove. Okay. So if it is a separable state, then it is PPT. It has partial. It's positive partial transpose state. Okay. Now corollary. If rho is not PPT, if it is not a positive partial transpose state, then it is entangled. This is a sufficient condition for entanglement. I mean, in general, finding entanglement is difficult. We have already seen something about the Smith rank being greater than or equal to greater than 1, strictly greater than 1. If it is separable, so using that we can see all the Bell state, but you can use this also to prove that the Bell states are. It's a good exercise. Okay, I mean it's in the you can look at that. So all the Bell states you can use this to prove that all the Bell states are also entangled. Okay? But we know it already from the Schmidt rank being strictly greater than 1. It's 2. Okay, because okay. So we will come back to entanglement later. Now we want to go back to our completely positivity. Okay? Discussing more on completely positivity. Okay. So let me summarize what we have done on CP maps. Okay. So this is the proposition. Maybe one thing I haven't proved. Okay, I will just prove that. Also, I will change the notation. Okay. Unfortunately, I have to change the notation. Okay. 1 n from A to B. This is a map. Okay? To say that n is something, n is a channel, and A to B, that is from L of HA to L of HB. Okay? Then just a linear map. Okay? Then the following are equivalent. 1 n A to B, okay, is a quantum channel. Quantum channel means it's completely positive and trace preserving. It preserves the trace. Okay. 2 n of AB. I mean, we have defined a matrix, okay, which we call it as gamma of n A to B. This is n, okay, n AB. Gamma AB is n of A to B, acting on that EIJ class, I mean, class IJ tensor IJ matrix, okay, which we call it as PN or something, whatever. Okay, this we call it as gamma n AB. This is not a state. This is positive. This is greater than or equal to 0. I mean, this is the equivalent condition for it being completely positive. It's greater than 0, and trace B of gamma n AB, okay, is equal to identity on A. This is the completely positivity condition, which is equivalent to this matrix being. This is the matrix in HA tensor HB. This is a matrix in HA tensor HB, and that has to be positive, which will determine that this is completely positive. The second condition, it should be trace preserving. That is ensured by this. We'll prove it. Okay. And I will just write down the other conditions also. Three. Okay. What is three? There exists Vi from A to B, no? HA to HB, such that n A to B of x is summation Vi x Vi star. This will come to here, that will go to here. So this is okay. And we approved this. Vi star Vi equal to 1. Okay. This is 1 on Vi from here to here, and it will go here. So 1A, right? 1A, 1A, 1A. So this is right, 1A. Then the fourth condition is there exists an isometry U from A, HA to HR tensor HB, okay, for some R, for some HR, finite dimensional Hilbert space HR, such that this N, which is actually given by U x U star. This is what is called isometry, and this is an isometry. Okay, U x U star. Then you take the trace over R. Okay, this is for all x. Yeah, we approved everything except that 1 implies 2, where the trace of this is. Except this, we approved everything. Okay, this is just I'm summarizing everything. So proof 1 is equivalent to 2. Okay, we approved everything else. 1 is equivalent to 2 except that. 1 is equivalent to 2 also. This is completely positive map. If and only if this is positive, that we approve. So if this is trace preserving, we have to prove this condition. Okay. So suppose one way, this way, suppose N is trace preserving. Okay. Then of course, what do you have to do? Then we want to consider the trace of that, right? So we have this gamma of AB, gamma. I mean, this gamma is used for EA tensor EA, summation EA, the maximal entangled vector, EA tensor EA also. But that, I mean, it is just the image of gamma. There is this EI tensor EI, summation, maximal entangled vector. That vector is what is called usually gamma. But if you take the pure state corresponding to that, theta, this positive map acting on the pure state is what is this gamma is. Okay. We are using the same notation. So AB on this N. Okay. Okay. So now we want to say that it is trace preserving, right? Okay. Now we want to prove. I mean, we assume that it is trace preserving. Then we want to prove that this trace B of this is this. Okay. Okay. Now we want to take the trace B of this. Trace B of this. We want to compute this. So this is just equal to trace B of, that is nothing but summation over ij, okay, tensor of n of this ij. Okay. Now trace B is just taking the trace here. If we take the trace here, only when I equal to j, that is going to be, I mean, otherwise it's 1 when I equal to j, otherwise it's 0. Okay. So I equal to j here means here also it will be I equal to j, because this tensor comes with that. So this is just summation. If you take the trace, this is a summation I, which is equal to I mean I. You have taken the trace. This becomes scalar. This has become scalar. Okay. This is just 1. Okay. That is clear. You take the trace on the second component. This is scalar. This becomes scalar. So it is this dimension only. But only when I equal to j, this is 1. I equal to j, it's 1, otherwise 0. Okay, so this is the summation I, which is 1. So one way we have proved. We have to prove the other way only. Okay. So to prove this way, that is, we have trace B of what is that, n? Trace B of what? Gamma. Gamma n AB. Okay, whatever that matrix is equal to 1A. Okay. Then we want to prove it is trace preserving. That's what we want to prove. Okay. We have, if you remember, we have proved that. Prove the following. We have n of any x is equal to trace A of x transpose tensor 1 gamma of this, whatever. Okay. If you remember, we proved in the last class. Okay, we proved something like this. I will come back to this. We actually, I mean, we proved this, and I said it extends to one tensor theta also, one tensor n also. We will go through that again and give it an assignment if it is not very clear. Okay, it is easy, but you have to. I said you have to linearly extend or something. We will come to that later. But this we prove. Okay, rigorously we prove. Okay, so n, this is equal to this. Okay. Okay, so this is how any completely positive map will look like. Okay, we just computed this. Okay, now we want to prove that we want to compute the trace of this. Trace of n, I'll just write n of x is equal to, so you have already taken one tensor A. This is just the trace on B. I don't write B because that we are using it for partial trace. So I just write trace, but the trace is on B. Okay, because already we have taken the trace on A. Okay, of this trace A, of this X transpose. So trace acting on trace of B is the whole trace, right? Trace of B acting on trace of A is this trace on the whole thing. Trace on the whole thing again is equal to trace on B times trace of A, right? I mean, trace of A times partial trace B. I mean, this trace is something like trace tensor trace. If you have taken one of the trace, it becomes just the it becomes a matrix on the other component. If you take the trace on that, you will get the trace on the bigger thing, further trace on that. Okay. On the other hand, you can do the first one and the second one also. So if you do that, this becomes, I mean, whatever we have here, whatever we have that, this is equal to trace. This is the trace on B. Okay, on B, L of HB. This is trace on L of HA. Okay. I'm not putting a because that is for partial trace. Okay, trace on L of B. Then you take the trace B, you can take. Okay, trace B of X transpose tensor 1. Okay, gamma of n AB. This is okay. Okay. Now you keep it here. Now if you take it, what this is just one tensor trace here, which is just the one tensor trace of this. The reason is, if you want what is one tensor trace, let me not write. It's going to be, it's clear. What is trace of one tensor? I mean, what is trace of B? You are just going to multiply one tensor I, right? On this side, okay, I will write it. This is equal to the same trace on L of HB times one tensor this I, okay, acting on X transpose tensor 1, okay, and then gamma, whatever that gamma AB, n, and here you have one tensor this I. Okay, that is how you compute the trace, summation I. Okay. Now this I will go here, and this I will go here. I mean, sorry, there is there is nothing. This I will come here. This I, when it has gone, you will get something which is scalar. When you apply all these things, you get something scalar. Okay. 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 Now you get, I mean, whatever you get is something in this component, you get scalar. If you want, you put another summation IA or something, summation AI. So you will get only the partial trace of this. Now what I am saying is this is always equal to trace of X transpose. Then there is the partial trace of this gamma of N AB. This is what you get. You just take this I, pass this, and you take it here. 1 tensor I, you will take it. Okay. So you will get only partial trace of this. That's what you will get. But that is identity. That's what we have assumed. Okay. So this is just trace of X transpose because that is identity in A. Okay. Well, this is taken on, I'm sorry. This, when you take the trace, this is HB. Sorry. This is HB, this is HA. When you have taken trace on A, you will get something on HB, so this will be HB. When you have taken trace on B, you will get something on HA. So this is HA. Okay. This is also in HA. Okay. L of HA. Okay. So this is just trace of XT, which is equal to trace of X. That is what we want to prove. We want to prove it's trace preserving. Trace of this is equal to trace of that. That's what we want to prove. So it's proved. Okay. So these are the 4 equivalent conditions for a thing, and we also have this criterion. We will discuss more on this later. Okay. Okay. Now I want to define what is called we want to discuss communication. So what is called something called complementary channel. Okay. So I want to define that. Quantum channel is something where you send a quantum state through some quantum communication carriers, wires, or whatever you call it as wire means it will not be this wire, but some carrier where this quantum state is taken from one place to another place. So it travels through space. Through space also it travels, and it also travels through time. Okay, so it changes the time, space both changes. So it goes to some other place. So usually in quantum communication and all this quantum computation, there will be one person because they introduce it's one person is called Alice, the other person is called Bob. Always this Alice sends something to Bob. Okay, and there is someone called Eve. Alice sends to Bob through a quantum channel. Okay, that is, they send it through something, but then it will interact with the environment. Okay, so usually that interaction with the environment will be an isometric channel. Isometric channel is just something looks like this. Okay. Whole universe, if you take the whole closed system, there you will be unitary. Okay, here this interacts with the isometric, so it's an isometric channel. Okay, so but then when Bob gets it, he will get only a part of it. Okay, he has means to get back this quantum state by doing something. Okay, that is, whatever, that's technology. So by doing something, so he gets it through a completely positive map. That is what this NA or something, NAB or something. But on the other hand, there is another guy standing here. He is dropping that. He is looking at that. So he will get a channel. He will get part of he will not get that channel which is going to Bob. He will interact with this through this. He will get something. That is what is complementary channel is. Okay. So whatever, these are all technical. What we have is the following. This is definition. Okay. Before definition, I will say is this. If you have a completely positive map, A to B, okay, from L of HA to L of HB, okay, then NAB, any X is equal to trace of R U X U star for some HR. Okay, for some HR. Okay, right? This we know. Instead, there is this LA to R X trace of A. Okay, this is what the E will do. He will take the partial trace with respect to A. He will get the other part. This is like getting the marginal conditional expectation. So of UX used. He will get it on this Hilbert space HR. So this is what is called complementary channel. Okay? This is what is called complementary channel. Okay. So we want to prove that we haven't defined. I just gave an example of complementary channel. We will define complementary channel and prove that it is unique up to an isometric channel. Okay? Isometric channel is UX U star. Okay? Unitary channel means if that U is unitary. As you can guess, we have already proved it. It is unique up to isometry. We already proved it. I will come to that. We have more or less proved. I am just going to use that in a different language. Okay. Definition. The channel n complement from A to say R is said to be complementary to n A to B, okay, if there exists an isometry, okay, U from, I hope I wrote the isometry in the right range, okay, from HA to HR tensor HB. Okay, it's an isometry such that NC you get it by tracing out that NC A to R X is equal to trace of B of UX system. Here I am not saying that this can be any isometry on any Hilbert space R. Maybe we can change to E if you want, because we used R for that particular one. So let us change to E. Okay. E is, I mean, E is for the, A is for Alice, B for Bob, E is for Eve. Okay. Whatever. So it's E. E is better. Okay. Then proposition. If n, okay, I will not write A to B and all. Okay, n A to E and n complement A to E prime are two complementary channels. To n A to B, okay. Then there exists a isometry. This isometry is different. U from E prime. I mean, it should exist between either E to E prime depending upon the dimension. I mean, if isometry has to exist from here to here, this dimension should be greater than this. Okay, so depending upon that, if the dimension is same, then it's unitary, of course. Dimension E prime is greater than dimension E. Okay, one of them has to happen. So it is depending on that. If direction isometry between U to E prime, such that you take the isometry channel, so such that n, so it is from E to E prime. So we want to get the E1, A to E, and complement of X is equal to U n A to E prime. This is like applying add U to this. I mean, if you consider X going to UX U star is an isometric channel, it is just you are composing with that isometric channel. By composing with an isometric channel, you get this. Okay. So this is from U star is from here. Yeah, it's correct. Okay. 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 So we have already proved it. We have already proved. So if I'm sorry, I will change this U to V or something. We already some U. We will use some U, so I'll change this to V. There is V also. We have V also. So let's use W. V we are using for the for whatever. Yeah, those operators, cross operators. Okay, X is a W. Okay. Okay. So I mean, we just have to write down everything, and it will be clear. Okay. First, N. So what does it mean? It means that both are complementary to that. N, I mean, N and N prime, E and E prime, N A to E prime, N A to E, both are complementary to N A to B. Okay, that means there exists an isometry. There exist isometries. Okay, U from A to HA to HE tensor HB. Okay, and U prime HA to HE tensor HB prime. Okay, we have this such that N is given by that, and N complementary channel A to E of X is equal to U. We need to take trace. Trace is taken, yeah. Trace A of U X U star. Okay, and N C A to E prime of X is trace A of U prime X U prime star. Okay. Okay. So we have all these things. Now, of course, we have an isometry. We can compose these two isometry. We get an isometry from here. Well, that's not the point. See, we have the following. This isometry U and U prime determines those cross operators by the following. Cross operators are those VIs. See, U is equal to some, it will look like this, V1 up to VR. Okay, where VI is from HA to HB. Right? Okay, this is how, where I equal to 1 to R. Okay, it will look like that. And we know that U prime is equal to V1 prime up to VR prime. Okay, where again VI prime is from HA to HB. Okay, now we know, we actually proved that for a minimal R, we have an isometry taking that to any cross operators. Okay, this is some R, this is some R prime. There is a minimal R. I mean, this is just any N of X, look like summation Vi X Vi star, I equal to 1 to R. The minimal R is what is called the rank of this. Okay, and for that minimal R, there exists an isometry of R cross, if anything, if you, I mean, this R is some R naught, let us say. This is the minimal one is R naught. Okay, there is an R naught cross R isometry which takes these cross operators, that cross operators we have seen. So there will be from one which takes you here, one which takes you here. If you compose the that star that, you will get an isometry taking from there. There exists a W in M R cross R prime. Okay, the isometry. Okay? This is just a scalar isometry such that summation Wij Vj is equal to Vi prime 1 to j equal to 1 to R. Okay, maybe the other way, R prime cross R. Okay, then it will work. I'm just summing over the column, no? So it should be R prime over R. Yeah. Okay. So we have an isometry like that. Okay. Now this isometry is from, now W is from, I mean, this is the dimension of this. W, you can consider W is from He to He prime. R is the dimension of, where R is the dimension of He equal to R. Dimension of He prime is equal to R prime. Right? That's what it is. This. That's how we constructed, if you remember, the so-called Stein spring. Okay. So this WAI from here. Now this should intertwine that. How it will intertwine that? That is because if you take WI, so what is this V complement? Let us see what is the V complement. So we want to say that N complement A to E, or the other one, IA to E prime, whatever, of X is equal to trace of, you take the trace with B of UX U star, right? I mean, whatever. U is the matrix, no? Whatever, UX U star. And U is made up of this V1 up to Vi. Okay. Now this is just trace B of, we have this V1 up to VR, X, V1 up to VR, right? So this is just trace B of this matrix, Vi, X, Vj star. I mean, this is just a matrix of matrices with the entries given by Vix, Vj star. If you take that, I mean, if you take the trace with respect to A, which is just the summation. If you take the trace with respect to B, it is just the trace of each entry. Okay. So this is just equal to so N complement A to E of any X is going to be this matrix trace of, this is just the scalar trace, not partial trace, of Vix, Vj star. Okay, this is what is this. Okay, and which is equal to, you have here. Now if you put a W here, you put a W star here, you will get the Vi prime, right? So that is what is that. Now if you have W N complement A to E, it's W star. Okay, that is exactly putting a W. I mean, that W, see, that W is a, this W, you can take it inside as a W with scalar matrices. W has a Wij entry, Wij times identity on that block. Okay, you can write it like that. Okay, that will be the tensor product of W tensor that, right? I mean, this is just, what I'm saying is this is equal to N complement A tensor E. Okay, this is a tensor product, but you have this W scalar product, scalar W here with Wij times the identity of that entry. Wij is a scalar, identity of the entry. So if you apply the W, you will get Vi prime that. That is how it is defined, right? This Wij is defined. Okay, Wij is scalar, but this is a matrix. So that is what you will get. So should I write? It's clear, no? Okay, if you have the W star, if you have the W star of that, you will get an E prime of X. Okay, we just apply that. I mean, you will get that, and you will take the trace B. Okay, that is because it is the W on the first component. Okay, and you have the trace B. Okay, so it's okay. Just verify this. Okay, just convince over this. Okay, we'll stop here.